So on to today's topic then, basement temporary works. So what is it all about? It's all about making space below ground when it's not feasible to go upwards or outwards, creating a basement. There are also other benefits such as increased security because we're being below ground. There's also no ugly imposing views, so you can put a big multi-story car park with only limited structure above ground without your neighbours getting the hump. There's also increased structural lateral stability because we're below ground and we can utilize the passive earth pressures around it to take the lateral loadings and also dampen vibration. These are just to name a few benefits really, but there are some notable points regarding the type of temporary works that would be required in a basement excavation. The first being that it is incredibly varied and really dependent on the existing structure. There is often a high level of risk because we are adjacent to roads, other buildings and infrastructure, rail, road, services behind those. There may be a requirement for underpinning adjacent structures if we are going deeper than our adjacent building and potentially undermining them. We are also working in the ground where there is traditionally a lot of unknowns and risk in the ground because we don't necessarily know what we're going to find when we go digging down there. There's also multiple disciplines all working in the same space. So we could have piling works, steel work, underpinning foundations. We've got all the different contractors associated with that. So a groundworking team, a piling team, steelwork fabricators, and all sorts of bits, and other disciplines going on at the same time, such as drainage, for example. There's the temporary works and the permanent works, acting some run the load transfer between them. So some could be acting in the temporary term and then moving into permanent, even though it's the same structure. And so we need to really understand the load transfer between them, the load paths, and who's taking responsibility for that. In a similar vein, there are multiple temporary states of stability as well, which is sequence dependent, and the potential for some slope stability issues as well, which we'll come on to in one of the case studies. We need to make sure that the temporary propping removal at the end of the sequence is considered during the analysis as well, because sometimes this can be the worst case depending on the structure that we're building. So it's important to take a step back and a holistic view on the sequence from beginning to end, not just, well, this is the propping going in and that's done. We need to consider the full story. Water can be quite a significant issue. So the hydrostatic head pressure on retaining walls can be significant. Just because the ground is saturated and the water is within the soil, it's if they're getting the hydrostatic head, then it's essentially like the wall, your basement wall holding back like a dam, holding back that water. There are some simple solutions which can be utilized, but it's understanding what the issue is of having water and the high water table in the first place, because the flotation on basements as well from the buoyancy effect of the water, a high water table should not be underestimated, but can be some significant loadings there. Retaining wall stability and global stability, the whole structure, not just individual elements and components of the design is important, but most of all, its buildability is absolutely key. The clashing temporary works is not a good look. We need to understand what the temporary works is and how it's going to interface with the permanent works to make sure we've got something buildable. So that engineering input is really key to enable a more efficient construction methodology. So let's look at some examples, some typical examples here. We've got the more domestic side, showing both the good and the bad. We've got some domestic buildings here which are being redeveloped to include some basements where we can't go up or outwards. Typically we go downwards. And we've seen first-hand effects of basements under construction, say in typical London terraced house, where there's been no engineering input, but we'll come on to that one. So on the left-hand side, we can see a very good example there. We've got the building where the superstructure, where they've identified that there is the potential for some movement in the walls and the wall plates. So they've got bricked up windows and wailing plates along the walls of the structure to make sure that, because we're cutting lots of holes in it, that the structure is going to remain stable. And then going From the ground floor down, we've got some good ground support there. So that's exactly what we want to see. What we really don't want to see is these photos that were taken on the right. And this is a property that James went to visit after it went seriously wrong. And we got involved afterwards. This wasn't our job, I may say. We got involved once the things started going pear-shaped, and we got called in to do an investigation. So you can see that there's some massive cracks opening out on the structure on the right-hand side, where the ground has been removed on the left-hand side, and essentially there's a foundation along that spine wall which has been undermined and is just following the path of least resistance and falling into the big hole next door. Is really very difficult to recover large cracks, large structural cracks like that. It's essentially like a big insurance job. It's a rebuild type thing. But this is the kind of thread in the shed type contractor getting in way over their head and not providing any support to the ground, digging it down, and then we've got some undermining going on there. So that's really not great. And then on to the commercial large-scale basement excavation jobs. A few examples here. We've got some really big toys here in basements. And what we're essentially doing is we're supporting the perimeter walls as we're removing the ground floor slab or the upper basement slab, which is providing a diaphragm support to that perimeter wall. We're looking at complex interfaces on boundaries that change on almost all elevations, multiple disciplines on one site, some pretty complex stuff really. And we'll show some case studies later on. On the right is Keybridge House, which James is going to take us through. And then on the bottom there is old Grenada Studios in Manchester. But the world keeps on turning as our basement job progresses. So this is another example of a basement job, and you can see that the world keeps turning. We've got cars, we've got infrastructure going around, so we need to consider the loadings from them and the considerable constraints that are put on our particular project from these activities. So roads, we've got a highway interface, which may well require an approval in principle, a report submitted to Highways Agency, basically outlining what the proposed solution is to ensure that the road remains stable, the road infrastructure remains stable, and that can take some time in terms of its approval. We've got adjacent structures, party wall awards and surveys to make sure that we're not undermining the structure next door, or if we're taking a building away and taking away some support, then what we're going to do to ensure that the adjacent structure remains stable. Underground structures as well. It could be chambers or underground vaults or underground roads or rail infrastructure that we need to consider. Services as well. What services do we have nearby, and will they be disconnected or do they need protection? Some services, such as cast iron mains, they can be very sensitive to ground movements, and if we are changing load paths or the perimeter wall loading conditions, then we may need to consider an assessment on ground movement to ensure that we're not going to overstress sensitive services such as cast iron mains or others. Because cast iron mains in particular are fairly brittle and hence don't really like a lot of movement. So we need to make sure that the work that we're carrying out in our basement aren't going to affect those. And then finally, crane loadings. So during the lifetime of the project, there's going to be a lot of material or plant that we need to be moved in and out of the basement, which is a number of meters below ground, which often requires some form of craneage. And these high point loadings from plant need to be considered and incorporated into the design of that basement support system. And so if we know what that is going to be, or we need to allow for that early on in the design so that later on we don't get caught out. I'm going to hand you on to James now, who's going to take us through some different examples of retaining walls and propping. So over to you, James.
Yeah, so time for notifications to pop up on my computer. So the scenario that we're going to be discussing today is the scenario that is the most common that we come across, where we're demolishing the structure, we've got down to ground floor level, and then we now need to remove the ground floor level. And this level is essentially, or has the ability to act as a prop to the retaining wall. So how we achieve we need to assess the wall to see if this is a requirement. And the first port of call is to review the walls to understand how they currently work. And often we receive no information on the walls, so we need core holes, local breakouts, trial pit to gather information on the walls. The ideal scenario being to prove that we don't need to prop the wall at all, but it's rarely possible due to the lack of information that's available on the wall. For masonry walls, these may span vertically from ground floor to basement slab or horizontally to piers or internal walls. Masonry has got a better capacity spanning horizontally, but when under compression from loading from above, from say a facade, this can flip and its ability to span vertically increases. So it's not necessarily certain how they initially designed the structure. Does this wall vary in thickness along its height? Where masonry gravity walls are used, these are typically a lot thicker the lower you go down. And what condition is the masonry in? And are there any faults behind? With reinforced concrete walls, we can determine if they cantilever or if they span floor to floor from a local breakout and checking the rebar that's in the wall. But this doesn't give us all of the information on overall stability of the wall. There are three main reasons we need to prop these basement retaining walls, and it's to prevent a local failure of the wall in bending or shear, to prevent an overturning failure of the wall, or to prevent a sliding failure of the wall. And as Josh mentioned before, also potentially to prevent movement of for structures behind the wall or infrastructure behind the wall. We must understand more than just the basic wall thickness or reinforcement information to provide an efficient design. We must understand how the stability is gained in the walls. And this isn't always readily apparent. For example, the two lower images show different basement wall constructions, both being reinforced concrete, but it's not necessarily readily apparent until you start breaking out those structures or doing investigation works, which way, how stability is provided to that wall. Obviously, there's other types of retaining walls as well as masonry and reinforced concrete walls, such as config and secant piled walls, sheet piled walls, and also concrete diaphragm walls. When considering loading to basement walls, we need to consider a variety of factors, which vary significantly site to site. Josh has just been through a few of these, but I'm just going to go through again. So firstly, it's pressure from earth, which depends on the type of ground that's behind the wall. When the ground investigation report is undertaken for a new structure, it's often missed. It often misses the information behind the wall because the Perna Works engineers are interested in basement level down, what's their new structure going to sit on, rather than what's behind the pavement or below the pavement or behind the wall. It depends on the type of wall as to whether this is a big issue and whether additional SI is required. If it's a structure that would have required excavation behind the wall to install, such as a masonry wall or something similar, then we can reasonably assume that it's a loose to medium dense backfill behind the wall as a worst case loading. But if it's a retaining wall, such as a diaphragm wall or sheet pile wall, understanding the ground behind the wall is important to ascertain the loads. Another factor that affects the load into the rear of the wall is the presence of a high water table, which Josh went through earlier. We also need to consider adjacent structures. Are there basements? Are there pad foundations for a neighbouring structure or strip foundation that would load our retaining wall? And is there any future temporary works that would surcharge the wall, such as a scaffold, gantry, a facade retention perhaps. And obviously loading from the roads, other infrastructure. There might be a requirement for an AIP if it's a road interface. Is there a requirement to locate a mobile crane in front of the wall? That would also need to be encompassed by the loading that we check on our structure. In addition to these loads, we also need to ensure our propping system is robust. So we potentially, there's a potential that debris impacts them during their life on site. So we need to consider this impact loading as well. So as I mentioned earlier, there are 3 objectives in propping for the propping system, which is to prevent a load failure of the wall, prevent an overturning failure of the wall, and to prevent a sliding failure of the wall. They will determine the positions of the support that we need to provide to the wall, but obviously there's many other factors to consider. Should we use raking props or flying shores, which I'm going to go through a couple of examples of each shortly. How can we locate the props to prevent clashes with the current and proposed structures? Whether we need to install thrust blocks or we can fix to the current basement slab. Are there any future works to replace or lower the basement slab that would need additional phasing or additional propping? Also, whether it's feasible to stage the new build works and propping works in a sort of sequential construction and demolition sequence to allow for an overall better, more efficient solution. There's lots of factors to consider. So I'm going to talk briefly about flying shores and then raking props, because there's several advantages and disadvantages to each. Flying shores don't introduce any vertical component to the wall, whereas a raking prop would impose a vertical reaction as well as resisting its horizontal reaction. So that's obviously something that's benefit for flying shores. Depending on the span, the flying shores may need intermediate supports, and often in very large basements, the props can become very large and take up a lot of room on site, making future works more difficult potentially. Flying shores are also susceptible to large loading variations due to temperature effects, which is something that needs to be considered. So on the screen is a couple of examples of flying shores use on schemes. Obviously, the right-hand side one is not for a basement scheme, but it illustrates exactly what a flying shore is. Raking props are typically more compact than flying shores. They can be adjusted to suit many site situations. However, they produce a vertical component which may cause issues, particularly when fixing into masonry, for instance. In that instance, we would likely have to introduce a tie-down detail, which I can go through an example of in a second. Raking props require either a thrust block or a surface they can prop back to at basement level. And I'm just going to go through a couple of case studies of some raking propping systems. So Manor Street, Bolton. This scheme was to prop an old masonry wall, and propping worked out to be more efficient to provide vertical supports at regular centres. And this also had the added benefit of allowing an easier installation due to the constraints on this site being quite severe in terms of access. The scheme required a large thrust block, which you can see in the cross section shown. We detailed this with the installation in mind. As I mentioned before, that was very critical to this project. So the installation sequence being initially to break out a pocket to the base of the retaining wall and put the horizontal section in place. And that was going to provide that uplift restraint for that vertical component that we mentioned earlier. Following that, the other elements can be installed on bolted to that horizontal member on site, and the concrete thrust block can then be cast around it, minimizing the amount of large propping equipment needed in a fairly confined space in the basement. The Majestic project in Leeds is the other example on the page. So due to site access being very good, is the exact opposite. The new slab and lower section of retaining walls could be built in advance of the demolition of the ground floor slab. So this allowed a very simple propping solution just within the structure to allow to the new basement retaining walls to allow for the ground floor slab to be taken out. This simple solution was a result of a collaborative relationship between us, our client, the permanent works engineer, and the permanent works engineers. And this allowed that simple phasing to occur. Onto another case study, which is the Bendigo scheme in Nottingham. So this example was where we were propping an existing RC wall back to the existing basement slab. Due to several complexities on site, there are a lot of different prop lengths and prop angles that had to be used. The photo below shows around a quarter of the site, just to give a sense of scale, so it's a pretty big project. Following discussions with our client, we devised an efficient system that worked much like a proprietary system to allow for reuse and provide flexibility on the scheme. So with components, they were all made in sort of standardized lengths and fitted together pretty much like a proprietary system would. We even developed custom sort of connections to allow easy installation on site based on past experience and projects, and a jack in detail to provide a degree of preload to the system. So proprietary propping or fabricated steel, I guess, is the question. The last few projects we've shared are all fabricated steel options, but that doesn't necessarily mean that's the only way of finding a solution. So at tender stage, we tend to provide client or initial concept stage. We tend to provide clients with an option both ways, and ultimately, it's a case of the length of time that the equipment is going to be on site and the overall cost of each scenario. Now, we often push for a proprietary solution because of reusability, etc., but this ends up being a client decision. And generally speaking, if they're going to go for the cheaper of the two options. Last time we ran numbers, the crossover between proprietary system and a steelwork system was in the region of sort of 10 months. So if it's going to be in place for 10 months or more, it's likely that steel would be the more competitive option. But I would take this with a pinch of salt due to the varying costs of steel, etc. This time frame. So I'm going to go for another example, which is a phased installation of phased demolition and installation of a scheme, which also had where the future project had a much lower basement level and required underpinning. So we've demolished our structure down to ground floor level, and we've installed a berm, and we've also installed whalers and knee braces at the top of the ground floor level in the initial stage. So the installation of these whalers and knee braces is going to allow for the removal of that berm, but those knee braces rely on parts of the structure that are going to come out. So there's a bit of complex phasing to go through. Josh, would you mind clicking? Cheers. So once the first level of whalers and knee braces goes in, that allowed for the removal of the berm and also the ground floor slab, and allowed us to start underpinning the structure, working sequentially along the wall. Would you mind clicking again? So following the underpinning installation sequence, it was detailed so that the a portion of the permanent works ground floor slab was going to be installed. And then we added the props back to this section of the structure, and that allowed us to remove some of the knee braces, I believe. Following the installation of these two props, we could then reduce the dig level down further and install another prop to the head of the underpinning. And then following this, we could reduce the dig slightly further again to the base of the new slab level and install the remainder of the infill slab. Following this, we could remove the lower prop and commence the installation of the first portion of the retaining wall, and then sequentially work our way back up, installing propping and installing a temporary prop and removing our propping as you go along. So it's quite an interesting little sequence of works there.
Thanks, James.
Yeah.
So I'm going to take us through now more of the benefit of the early consideration of temporary works in certainly in basements. This is a case study for Landmark Manchester. The benefits that can be taken from schemes like this they need to be considered quite seriously, and to get that constructability right early on. And we're going to take you through that. So this is a case study. It's based on the Bowman Kirkland job called Landmark Project in Manchester. I was the lead temporary works designer for the scheme, and it's a great case study really because it had so many different interfaces along each elevation that required different solutions. So it's more like several jobs in one. Our involvement on the job were the design and planning associated with the demolition of the former 1920s theatre, which was then later turned into an Odeon cinema. That's shown partially demolished on the top left-hand side of the screen. Then also we looked at the preliminary and then the detailed design of the basement propping scheme, because the new basement was deeper than the existing, so that's resulted in quite a complex solution being required there. We looked at the coordination and the sequencing of the removal of the temporary works that would enable the completion of the new basement as well, and then you can see the extents of that job on that aerial photo on the right. And once the basement was all completed and we were up to ground floor, then the design of various temporary works items during the superstructure construction. So we carried out the work for, to begin with, was directly for foreshore demolition, and then we worked directly for Bowman Kirkland, who was the principal contractor. Because we were part of the project team during the demolition stage, we were involved very early on, and this early involvement was key really to planning the construction of the new build and how the temporary works and permanent works could be cleverly designed to complement each other. So this is the site location. It's on Oxford Road in Manchester city centre. The central library is on the kind of top left, with Oxford Road railway station just down at the bottom. I've also shown a bit of a detail of what the building looks like on the right-hand side there. It's a 15-storey office building known as Landmark. The overall concept of the proposed development was initially illustrated on some very simple sketches. These were actually done by our very own James Dunlop on the presentation. And these were really done to communicate our idea of how we saw the whole redevelopment from the completion of the demolition. The basement had been backfilled, how we were going to turn this quite messy site into a nice clean basement. And at this point, the structure had been demolished and the basement had been backfilled. And what you can see in the pink hatches there is a high level platform that was been constructed, and that would enable the contiguous pile walls on the basement extension, and also in an area where the existing perimeter wall was too shallow to enable, or significantly shallower than the other areas, so that would we'd be undermining that part of the building if we were to dig down there. So there's some simple sketches which I'm going to take us through. So once the piling is completed and the earth berms are in, the next general stage was to install the central raft slab in the center of the site. That was the permanent works, and this was to be used as a base to prop off and support the perimeter walls. The tower crane bases as well were incorporated, and they could then be installed, which would really help in speeding up the process of installation and material movement. And there were 2 tower cranes on the job, which would facilitate the whole construction of the structure, not just the basement. Once the top level of props were installed, similar to the sequenced installation that James showed earlier, we could remove more of the berm structure, and then that would permit the construction of the underpinning and the remainder of the perimeter slab once we've got that lower section of props in. And we can see a section of that shown here with the underpinning on the right, on the left-hand side, and the props supported back to the main raft slab on the right. That was the general proposal. That was us selling the dream of what we saw. So that's the general idea in a very brief nutshell. Now we're going to go see how the proposal worked in action actually on site. So this is the initial stages here. So you can see we've got high-level pile mats and piling rigs working. We did incorporate some geogrid into those slopes so we could reduce the amount, or we could increase the slope steepness and reduce the amount of material in the body of the working platform. Prop installation was actually carried out in a balanced manner, working either side of that central raft slab so that we could ensure that the global stability of the system could be ensured. We didn't want to prop all along one side and find that our raft slab was moving along. That would be a little bit awkward. So key challenges that would be overcome during those concept stages and moving them into the detailed design was the coordination of the location of the props. That was quite tricky. Some sequencing of the props installation and fabrication drawings, and really general issues born out of trying to be as efficient as possible. And that last one seemed a little bit odd, but we strive to reduce the amount of temporary works on site, and in doing so face some significant challenges. And these are namely justification of the really variable existing structure, the design collaboration with other organisations such as Curtains, who were the structural engineers and permanent works engineers for the project. But that effort really paid off with reduced material usage and the faster construction time. It does take longer to use what we've got and be resourceful using the existing structure as opposed to bringing in some nice big props. And similarly, it also takes longer to prove that the big props or the permanent works in the temporary condition is suitable. But that effort early doors really does pay off with dividends such as time and money on the project, which is when it really matters, when we've got a very busy site with not a lot of space. So we can see the propping in more detail here. There are generally 4 areas, typically raking props to soldiers to walls. But then the other 3 areas, we've got the contig propping to the north, the temporary contig propping, and then some flying shores as well. Because we were propping off the permanent works in most places, we had to have the propping designed and ready well in advance to enable the permanent works to be detailed and constructed. So having the system designed and ready meant that we could take advantage of all sorts of ideas and make the construction quite a slick process. It's the idea of don't be a slave to your designs, make your designs a slave to what you want to do. So let's start with the raking props. We can see an elevation of the typical propping that was used. We used vertical soldiers just because that supported the construction type on this particular project. And those soldiers were supported by tubular steel props that had proprietary adjustable jacks just to allow for some length tolerance. And then the jacks were fixed back to a fabricated bracket, which was incorporated and anchored into pre-made pockets in that raft slab. So it was nice and simple to install. And this system used the vertical soldiers as opposed to the horizontal whalers. And those vertical soldiers were anchored into the wall there. And that was a composite soldier design. So we anchored the PFC to the wall at regular centres. And that was to mobilise some of the wall's capacity as well as the steel in the PFCs. Hence it being both masonry and steel, hence it being composite. And this meant that a much smaller section could be used. That was so important because a more traditional approach or a non-composite approach would have seen a much deeper section, which would have led to a significantly thicker line of wall or piers at regular centres, which would compromise the internal floor area in the basement. And it would also require more concrete too. So as we were working on the design well in advance of the construction, we worked with the permanent works engineer quite closely to detail a soldier that could be incorporated into the new line of wall that was shown there. Even that the non-composite on the left-hand side, I'm sure if that could work with the piers, because the rebar detailing would be pretty difficult. And here's a slightly younger me stood in front of that system there, and you can see the soldier on the right hand side. We've got some underpinning there on the right hand side underneath the soldier, because we were going deeper than the existing wall, and then also some propping to the contig temporary contig wall as well. And as the contig wall was temporary, it didn't need a capping beam at the top, so we did away with that and just had some wailers. In the corners of the structure, we used some horizontal shores or some flying shores, and this was based on a similar design approach as the raking props, using a composite soldier at the supports. But because we were positioned a fair distance from that central raft slab, and we were in the corner, we utilised some flying shores here. All the props were located to minimise clashes with walls and columns of the permanent works, so that required some synergy between our designs and the permanent works design as well, for all different types of props, including the capping beam propping too. So this is the capping beam propping on the north elevation, where the basement extents was extended. So we had a new area, and a new contiguous power wall was constructed and the capping beam propped. And that design that we've shown there showcases how we were able to incorporate some pockets into the capping beam to receive our prop base plates, and again work with the permanent works engineer to establish what that capping beam was good for in the permanent case, because in the temporary case, it didn't have that grey line that you can see on that elevation there, which was the ramp. So it was, in its permanent case, it was pretty much continually supported. However, in the temporary case, it was supported at points. So we needed to make sure that that capping beam could span between the point supports in the temporary term. It was actually working harder in the temporary than it would have been in the permanent. So we had some input on terms of the rebar. And also, as we were having an input in the rebar, we detailed some pockets as well, so, and holding down anchors, so that it was nice and easy to install when it went in. In a similar vein, I'm going to show you the base brackets as well, the raking props, which are located here. These were specifically fabricated brackets that were designed to feed the forces from the raking props into that central raft slab. We've got a snippet of the fabrication drawing here, what they look like. And then as we produce those and the pocket locations and the setting out drawing for the permanent works engineer, this enabled the rebar detailing in the basement raft slab to accommodate pockets and then those cast-in anchors similar to the capping beam. The pockets reduced the loads on fixings and shear that was taken by the direct bearing onto the reinforced concrete pocket. So we're not just purely relying on the anchors. We were basically butting up the bracket to the back of the concrete pocket, so it was going nowhere. And that's a really good example of risk reduction through design that was made possible by getting involved early on. As the new basement was deeper than the original, then we needed to underpin. But this underpin served as both a temporary retaining structure and also a vertical support to the walls. So that's why it's got some reinforcement in its front face. The reinforcement tied into the structural blinding as well, which acted as the lowest prop support to the central raft. And then these underpins were constructed in hit and miss fashion, as per your typical kind of domestic type of underpinning, but this was on a much larger scale. And this hit and miss sequence ensures that there's enough soil left in place to provide support in the short term during the construction of those pins. And once all that was installed and completed, then we could get on with the job of constructing the rest of that basement slab and then some of the walls that were sprung off of that. So at this stage of the project, all the temporary works that had been designed had been installed. So the next role we played was collaborating with the project team to control the removal of the propping once it became redundant. Meticulous control was required here, considering that we were relying on that new structure to provide temporary support in places. And this was managed through sequence drawings, detailed 3D sequence drawings, and also lots of site visits and site inspections. As you can see here, it was quite close in places, but utilising the doorways and risers meant that the box outs around props and then the subsequent making good patching up at the end of the job, they weren't required. The coordination in the design early on meant that this was possible. There were some areas which we couldn't avoid, such as where the raking props went up through the B1 and the ground level. But we tried to locate those in areas where it would be easy to put some lapped reinforcement patches to make it a bit easier. And you can see some of the images here where we've got the composite soldier in action as well. It's quite a deep basement. So overall, our involvement in that project enabled the demolition, reduced level dig, basement construction, and then finally the remove of the props and ultimately the construction of Landmark Manchester, the superstructure. In summary, it was quite a complex project. It had many interfaces on all sides, including along the bottom because we were in sandstone, which held its own challenges. We used as much of the existing structure and the permanent works as possible so that we could provide that efficient solution which would reduce the amount of overall temporary works, which the site team were very happy with. And we tried to strive that mantra of no temporary works is the best temporary works. That's not saying if you need to put a prop in there, then you don't put the thing in. It's thinking, can we be smarter and slicker about this whole process of constructing what we need to have in eventually and sequence it so that we can do away with some temporary works, which is essentially just an overhead for the contractors who's constructing it. So this process of our early engagement enabled that simpler and slicker installation, leading to that reduced cost and program savings and constructible efficient solutions. And this is especially important in basements where a great deal amount of resource and time can be wasted in delays. I'm going to hand you now on to James, who's going to take us through a Keybridge House case study. So over to you, James.
Yes, so Keybridge House was quite a while ago now, but it was a very complex scheme in terms of the analysis required and in terms of coming up with good concepts and how to approach it essentially, because there's quite a lot of complex issues such as clashing with the demolition of the current structure and the installation of the new structure due to the site constraints as to what the permanent works were, that the propping requirements were very constrained in where we could put them essentially. So the load path is detailed above, where support is provided by the ground floor and 2 basement levels. Each basement level is around 6 meters high, and the retaining wall is a concrete diaphragm. The wall is located along the line highlighted in red on the right-hand side of the screen in the Google Maps image. That image is the new structure back in following our works. Highlighted in the pale red on the left-hand side of the screen is a cross-section through the structure that shows, or a plan through the structure that shows the extents to the demolition works. So we're not entirely taking the slabs out, but we are taking the majority of the slabs out. And the green is the new structure that's going to go in. So ideally we don't clash with the green. And also there's a lot of lift cores and things that are being taken out as part of the works as well that we also can't clash with. So to enable the demolition of the slab, we had to look at both vertical propping to pick up the edges of the slabs that were going to remain, and also reviewing the lateral propping requirements and devise the most efficient way to provide this. One thing that made our analysis particularly complex was that we allowed in our analysis the stiffness of and propping from the remaining slab that was going to remain in place, because that's obviously going to add a lot of stiffness to the structure and also reduce the lateral loading to any propping system. This is one of the concepts that we provided for the scheme, which used a small number of very large flying shores to prop across the void, essentially. The reason we could get away with such a large spacing was because of us considering the amount of structure that was going to remain in and the slabs acting essentially as beams. Ultimately, we detailed the system with flat jacks at the centroid of the slabs, and the props were above and below the slabs. So half of each flying shore would have been above and below, which meant the line of action, the propping line of action, was within the center of the slab. And it also enabled an easier installation of the scheme before the demolition works. But ultimately, this option wasn't chosen by our client due to the inevitable clashes with the permanent structure. The final solution that we ended up with was a combination of raking props and flying shores. So the basement B1 level was generally propped with raking props, and the ground floor level was propped with flying shores. Now, the propping at the ground floor level was much less due to the increase in pressure at the lower level. So that the larger props that's doing the bulk of the work is the raking props, and you can see on the right hand side of the scheme, the right side of the screen, the load path, as it were. So here are a few photos of props as installed on site, along with details of the base plates and connections into the whaler. The vertical component resisted, the vertical component, with there being raking props, was resisted by large anchor plates that was grouted tight to the retaining wall. With it being a diaphragm wall, the walls were not exactly perfectly straight, which meant that particular attention to detail was required to prevent overloading of the anchors. And in fact, a survey was completed at the whaler level all the way along to determine the best positioning, the best positions for these anchors, and make sure that this was adequately considered. So the whaler was pushed into these anchor plates by the prop, which was attached to a stiffened section of the whaler, which was to ensure that the line of action through the prop didn't cause any issues such as rotation to the whaler itself. This connection also allowed for the system to pivot, providing flexibility and enabling a more simple installation process. The system was preloaded from the base of the props with hard jacks, and the load was then transferred to the outer bolts, and the hard jack was removed, and then the whole system was shimmed and grouted up. And that's it from me on Keybridge. And I think that's back to you, Josh.
Okay, thanks, James. So our final section of today's session is going to cover a little bit about how site investigation can, if done early on, can really drive some effective temporary works. This project is a great example of where good site investigation led to a significant reduction in what we thought that we would have to do when we looked at it at tender stage. So the job's old Grenada Studios in Manchester. It's a basement redevelopment scheme that we worked for Bone and Kirkland in Manchester. And it included the redevelopment of the existing basement, digging down a fair depth in some areas to enable construction of some pretty big pile caps. There is I could talk about this project for a lot longer and run through all the different areas, but I'm going to focus on the interface that we had on a particularly tricky elevation. So this area is the interface between the site and an underground canal that was then redeveloped into a bomb shelter with blast walls and was just a historic relic on the boundary. Shown here is the concept temporary works that would have been required, because at the point of tender and the concept stage, we really didn't know anything about that adjacent canal structure other than it was there somewhere. Basically, we're propping for the full horizontal thrust that you get from the arch, because there was at the soffit of the canal was an arched ceiling, which then supported a road which would remain open for the adjacent site. So there's a quite significant horizontal thrust that we'd get from that arch, which we needed to deal with. This scheme here, it includes 6 large heavy-duty props. They're at regular centres, and quite a long steel whaler beam as well. This solution would have really inhibited the site works, making room on an already quite small footprint of a site very tight. And it also relied on some very specific and controlled sequencing of the installation of the permanent works, which similar to which we did at Landmark, where we installed the basement slab in stages. We didn't really have a option at Landmark. Yes, it is quite difficult to do, but it is possible. But we try to avoid that where we can, and try and keep the temporary works significantly reduced and out of the way where possible, because it's much simpler. Yeah, that's what we had at the start, because we had very little information on what was there at tender stage. So that's the kind of system that we were looking at. So here's a closer look at the plan and on the proposal that we had in the end. The area supported a road at ground level and had an interface with that underground canal that you can see running through the left-hand side of the site to the south. Once we got onto the job, that meant that we were able to carry out several surveys, lots of site visit, and what seemed like endless hours watching endoscope videos on my behalf. That was required to draw up the structure in 3D on Revit. And this enabled us to understand the structure and therefore understand the loadings that would be acting upon the basement wall during the works. And you can see the structure that I drew up here. And we found that there was a former canal tunnel was part of the Manchester Underground Canal network. And this area had been repurposed as a bomb shelter. And you can see the series of those concrete diaphragms that were used as blast walls, presumably, and then the concrete infill on the ceiling as well. And that meant that, in actual fact, the horizontal thrust from the arch was actually really quite small than compared to what we were expecting previously without those diaphragm walls in there. And so the structure was relatively stable in this state. So the rationale behind the temporary works design was therefore to utilise as much of that existing structure as possible to minimise propping and other temporary structures that would become redundant once the new structure was built. And this follows our kind of mantra and efficiency motto of no temporary works is the best temporary works. So we can see the final solution here on this page here. So we've got some diaphragms between the corridor that you could take from the existing basement through into the canal network. And we're filling in those doorways with some temporary props to provide a diaphragm and therefore keep the wall stable so that the load path goes from the arch through the concrete blast walls and then at an angle kind of down through into the structure and into the sandstone below. In other areas, we filled in doorways and then also constructed a wall to provide that diaphragm on that elevation as well. We can see a couple of examples of the steel frame diaphragms that was installed, and they were anchored to the walls and effectively enabled that transfer of loading down to the basement slab and therefore the sandstone. And because the temporary works installed in this area were way up the way of the permanent works being constructed, there was quite a simple interface here. And generally, it's install the props and the diaphragms, demolish the structure, construct the basement structure, and then simply remove the diaphragms. And that simple interface meant for quite traditional and fast construction methodology of the permanent works in that area as well. And that really demonstrates, in kind of case in point, that thinking ahead and getting some good information about the structure around you can really pay dividends later on in the project in terms of reduction in temporary works and increasing in time and delivery. So I think the projects that we've highlighted today illustrate to me how important it is to get the correct methodology in the first place, which is absolutely critical for those complex basement redevelopment schemes. The right methodology changes from job to job and also client to client, which is why those good kind of trusted and understanding relationships between the project teams lead to good, successful projects, and good in this case meaning safe, successful, and projects delivered on time. And we work with many of our clients early on, even at tender stage to provide that engineering input, but it doesn't necessarily need an external consultant. It needs just the time and engineering knowledge or input in thinking of how we're going to plan this project so we can get to the right solution for a complex project and save on some time and money and carbon or whatever the driver may be. But planning ahead certainly does help us out on a project. That concludes our session today, but it's certainly not everything you need to know about the subject, not at all. There's plenty of information out there. There's some really good resources provided by the iStructE. There's the Temporary Works toolkits on various items, including some basement propping schemes. There's lots of guidance from Syria as well, various guidance. I've put some screenshots in there. There's a publication by the ICE, Temporary Works Principles, and also the Temporary Works Forum. There's a plethora of knowledge on there. It's a good resource. They can all really help you de-risk that tricky basement project, which you may well have. After all, knowledge is power.